We also publish a version of our technology strategy. So internally, we have a H1, H2, H3 look at where we think technology is going over the next 2 to 10 years. So, metaverse, woo, quantum, woo. And we published this internally, and then we thought maybe we should do it externally. So now we publish something called The Looking Glass, Alice in Wonderland and Through the Looking Glass. And that's our public-facing view of where we think the industry is headed, where technology is headed. I'm not going to talk any more about Thoughtworks. You can find us at the booth. I'll be hanging out there all day. You can talk to us there. That's my contractual obligation done. So now I'm going to do a brief recap on Lego. Is there anyone in the room who doesn't know what Lego is? Bueller? No. That's good, because I don't need to do a recap on Lego. But I will do a recap on Star Wars. So not everyone has seen Star Wars. So I should point out that there are spoilers here. So if you haven't seen Star Wars, you might want to close your eyes or something. So episodes 1 to 3, this is where we start with Star Wars. Yeah, we don't really talk about episodes 1 to 3, if you're a fan, right? This is just, it didn't really happen, episodes 1 to 3. Again, we all went closed our eyes, 1 to 3. Then we have episode 4. In episode 4, a boy realizes he can do magic, falls in love with a girl, and kind of sticks it to the evil empire, blows up a big space station, incidentally kills tens of thousands of innocent stormtroopers, which is, awkward. Episode 5, the boy's mate gets frozen. That sucks. The boy learns how to do magic. He finds out his dad runs the evil empire. Episode 6, the boy understands that he loves the girl as a sister, which is lucky. Could have gotten very awkward at that point. Basically, boy fights dad fights boy beats dad, old cackling guy, the emperor does the thing, and his dad saves his life. It's wonderful, right? So nice happy ending, except his dad dies. Episode 7, right, there's a girl that realizes she can do magic. It's quite exciting. She falls in love with a boy, sticks it to an evil empire, something bad happens to one of the people from, one of the heroes from the earlier films. That's the spoiler. Episode 8, the boy is back, except he's old and really grumpy. This is the boy from episodes 4, 5, and 6. He drinks puffin juice, which is like green or blue for some reason. There's no kind of explanation for the puffin juice. Blah, blah, blah. And then, oh my God, no, not Leia. Oh, no. Episode 9, wait, what? He was like totally dead. The cackling dude with the electricity, I'm sure he died. That's really strange. But no, he's back. There's another space station that builds up. How did he build it? Etc., etc., etc. I am all the Jedi. Cool. That's Star Wars in a nutshell. Everyone clear? No, not too many spoilers, I hope. No, good. So recap on flow. What do I mean when I say flow? This is something that's taken me all of my career to really understand. I think it's the thing that underpins all of Agile software development, all of extreme programming, all the way we try and get stuff done more effectively these days. It underpins microservices, it underpins team topologies, it underpins continuous delivery, flow, the flow of stuff, whether it's ideas from a business person through a development team into production, whether it's the flow of oranges from a field onto your table via a supermarket, whether it's the flow of raw materials through a factory and then being turned into a car. Most of what we do as software developers, as working on teams or other roles on teams, is thinking about managing flow. How do we get better at managing flow? How do we get better at getting into production? How do we become more effective at putting our software live? How do we do that from moving from 3 months to release to 1 month to on demand? It's about flow. Basically, it's about system optimization to keep stuff moving through whichever system of work that we happen to be in. This is my definition. Yours might vary. Others have other definitions. But this is my definition. System optimization to keep stuff, user stories, requirements, whatever they may be, moving through a system. Briefly, me, that's my cuddly toy. I wrote a thing about microservices, as Dan intimated, so apologies for that. That seems to have taken off. That was back in 2014. More recently, I've been writing a bit on Martin's site with some of my colleagues around legacy displacement patterns. What do we mean by that? Well, you've probably come across the idea of the strangler fig pattern. Everyone says, oh, we need to move away from legacy. We need to migrate off this platform to another one. We'll use the strangler pattern. We'll strangle it. But that means about 50 million different things. So what we're trying to do is put together a pattern catalog of how exactly you go about doing that from a business perspective and from a technology perspective. So breaking the patterns up into things like event interceptor and blah, 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 blah. Have a look. It's interesting, if you like legacy. I'm also a massive nerd. You might have guessed this. This is me and my son visiting Warhammer World in Nottingham, where they make the little space marines that I collect and paint. That's the intro over. Now, witness the firepower of this fully operational Lego and Star Wars-based conference talk. Well, it wasn't actually a galaxy, right? It was an office. A long time ago in an office far, far away, Thoughtworks, London, we were given, as a thank you by Lego, who we did some work for. In fact, the work we did, they were building a massively multiplayer online game. I think it was called Universe, or maybe the precursor to Universe. And Lego had a bit of an issue, because the way the world works, in Lego games, you collect little bits of Lego, then you build stuff with them. So in this game, you know, you're a 10-year-old child, or 13-year-old or whatever, and you collect all this Lego, and in your local client, you put some Lego together, and then you build a structure, maybe a house, maybe a bridge, and you publish it. Then everyone else in the world can view it. Now, if you look into the dark mind of teenage boys, you might understand what the first thing they might try and build with lots of Lego in a computer game is. Essentially, Lego had a problem with genitalia detection. Because the first thing everyone would build was kind of, yeah. So they asked Thoughtworks in to help them with optimizing their detection mechanism for this. And as a thank you for helping them out, they sent us a big box of Lego. And this is the story of how a team of Thoughtworkers built the Millennium Falcon. So episode 4, a new box. So this is the box. This is the original 10-year-old version of the Millennium Falcon in Lego. It was, at that point, the biggest set that had ever been built, the biggest Lego set ever. If you look at this, it's recommended 16 and over, 16 years and over to build this. That's quite a complicated box. It has 300 double-sided pages in the manual. It's like yay thick, ring-bound. This isn't the biggest, by the way. The new ones are so big that they come in a box with wheels. Because they're so heavy, you have to wheel them along like a suitcase. That's true. But still, this was at the time a pretty big Lego box. It had over 5,000 pieces, and the key thing is all the pieces are stuck in the box in one sort of place. This is our team. You can tell who I self-identify with. It's Chewy. This is a team of Thoughtworkers who we were benched, if you like. In consultancy terms, we were in between projects over a Christmas. In Thoughtworks, because we're hippies, we call it being on the beach, but we were in between projects. So now, okay, Lego, Star Wars, Millennium Falcon, fantastic, but I did mention flow. So I'm going to do a little bit about some of the, I guess, the science, if you like, behind what we do. Some of the tools and mechanisms we can use to help us optimize our systems for flow. So the first thing, and I appreciate I'm probably preaching to the converted here, but it's worth sort of reflecting on these tools. The first thing is a storyboard or a Kanban board where we track requirements of one form or another. Maybe that's product definitions, user stories, epics, from creation through into deployment. And typically we have cards, which are stories. We have swim lanes. We have, in development, we have ready for development, we have in analysis, these kinds of things. That's a storyboard. I'm sure most people have come across that day to day. Then we have burn-up charts. So unlike Scrum, in Thoughtworks, we tend to burn up scope. We don't burn down scope. So we have a total scope that we move up to. Obviously, in product development, you're never done. And this is why burn down charts are problematic, because you hit a kind of an end. Well, often there is no end in software. We add scope, we increase the amount of stuff that we need to do, right? So we burn up to that scope. This is something called a cumulative flow chart. And we're starting to get into the more esoteric project management tools, or tools for managing flow here. So a cumulative flow chart is a bit like a burn-up chart, except you measure how long it takes each swim lane, a card to move through each swim lane. So each of these represents, in development or ready for development, and so on. And what this allows you to do is find blockages, find which parts of your overall process, which parts of your system are need to be optimized to improve flow. We then have something called a value stream map. This is popularized by lean manufacturing, more or less. This is the idea that we track our activities through our system of work. So you can think of it as the swim lanes, but measuring the amount of time it takes for each activity to be performed. So in this case, we have, say, a user story that takes 3 days to get done, 1.5 days to be tested, half a day to be deployed. But what you see in the steps in between is, in between development and QA, it sits there waiting for 10 days. In between QA and deployment, it's a month. So in terms of actual effort, you've got, 5 days of effort, but it takes 47 days for value to be realized. So value stream maps are super interesting because they allow you to see where in your system you can go first to try and optimize things. The wait times we talk about, value adding and wait times. The next thing, and this is something that many people don't or haven't come across, this is something called a control chart. So unlike the burn-up, where we track cumulative scope, what we do in a burn-up chart is track the amount of scope we've completed every week. And then we look at the variability of that number. So if you've got a team of 5 developers or so, and every week they do sort of 7 points, 9 points, 11 points, 8 points, 11 points, you shouldn't shout at them if they do 7 points. That's just the natural system in which they work. And you can understand that and understand what the control limits are, if you like, by tracking 3 sigmas either side of your average velocity, the amount of work you get done. And that's what those lines are: upper control limits, lower control limits. If you're outside of that, something's wrong. If it isn't, that's just how the team works. Incidentally, this is where Six Sigma comes from, the lean optimization process, methodology, because those control limits are 3 sigmas, 3 standard deviations either side. Back to the Lego, thankfully. So episode 5, the Lego strikes back. So the first thing we did, we took a look at the box, right? There's 5 of us, we took a look at all this Lego, we're super excited, and we all jumped into the box. We're like all piled in, woo, it's Lego flying everywhere up in the air, like a big Lego fountain, like a chocolate fountain made of Lego. Super excited. And then we all put the bits together, right? We started off with the first page of the manual, all found stuff, all put stuff together. It was really good fun. But it went really, really, really slowly. So we had a burn-up chart, obviously, and we had a value stream map of the activities we were performing. And this is what the Lego system of work looks like on a value stream. So we have 2 value-adding activities, finding stuff and putting stuff together. It was taking a really long time to find everything. Everyone was like looking around and blah, 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 blah. So that's the first tip. Understand the system that we're working in. Visualize what's happening as we're working. The main difference with what we do as software engineers, developers, and associated roles is that the work we do is invisible. It's knowledge work, it's information. It's a set of requirements that have turned from, an abstract idea into something more concrete, but it tends to be invisible. And so the system of work in which we work in also tends to be invisible. If you're in a factory, it's quite clear what the system is. Raw materials get turned into a widget, that widget gets turned into more widgets, and finally you get a product out the other side. You can see what's going on with physical manufacturing, or with a supply chain. You can see lorries on roads. With what we do, you can't. You can't see the work. So that's the first tip. Visualize the system that you work in. Understand it. And what we were doing is processing our work serially. So we were all finding something and then all putting something together. Processing it serially. That's my next tip, is let's use this idea of storyboards to make the invisible work visible. We often kind of cargo cult, around different tools and techniques, but there are underlying reasons for them. The reason for a stand-up meeting is not to tell people what you did yesterday and what you're going to do today. The reason for a stand-up meeting is to understand if there are any blockers that people can help you with to improve the system of work, improve flow. And it's the same with storyboards. There's a reason we have these things, and it's to visualize the invisible inventory, the invisible work that we work on day to day. The result of us processing this work serially was we were going really, really slowly. So essentially, we weren't going to be finished until the heat death of the universe. That kind of sucks, right? Because we only had about 3 weeks on the beach. Didn't have until the heat death of the universe. Boo, sad face. So this, I said it's 10 years of technology, or 10 years of Lego. I first did this talk about 10 years ago. And this was before memes. So you can tell when the more modern stuff appears because memes happen, as opposed to emoticons. Anyway, so sad face. Episode 6, the return of the processed Jedis. So a funny thing happened. We have our system of work, finding pieces, assembling pieces. We were moved from basically everyone doing one thing and then everyone doing the next thing. We stopped doing that and we started doing something else. We started having some people finding pieces and some people assembling pieces. And we were doing that at the same time. See? This is us. This is a visualization. This is exactly what it looked like. What we've done essentially is identify a constraint in our process. It was taking a long time to find these bits of things in this box. So we understood that there was a constraint there, and then we need to optimize for the bottleneck, optimize around the constraint. Essentially, it turns out what you can do to elevate that constraint is find bits in parallel. You don't have to have people finding pieces, then assembling pieces. You can have lots of people finding bits at the same time as people putting stuff together. So that's my next tip. Use the theory of constraints. So the theory of constraints comes from a brilliant book, novel, business parable, if you like, called The Goal, written by a management consultant named Eli Goldratt many years ago. It was rewritten fairly recently as the Phoenix Project about IT, about what we do. But originally it was about manufacturing. And in that book, in that parable, that business parable, Eli Goldratt comes up with this idea of the theory of constraints. In any system of work, there is always going to be a bit that goes the slowest. What we need to do is identify that piece, identify the thing that's going slowly in manufacturing, the machine that's going the slowest, and optimize around it. Identify the bottleneck, use the theory of constraints to optimize. The example here is in the book, the famous example is from the scouting movement. So if you're in the Scouts and you're on a hike, there might be someone who's a bit slower than everyone else. So how do you optimize for the whole group to get to the end? Well, you subordinate the whole group to the slowest member of the group. And you have the slowest person at the front and everyone walks behind. And that's what we do in manufacturing. You only operate at the rate of the slowest machine, at the rate of the bottleneck. But once you've identified the bottleneck and once you've You've worked to make that bottleneck go as fast as possible. It's like that game, in the fair where you have to kind of hit something and another thing pops up and you hit it again and hit it again. The bottleneck will move around. So you continually optimize looking for bottlenecks. So remember what you learned about queuing theory, right? I don't know if you've come across queuing theory or done much in the way of computer science and queuing theory. But in queuing theory, funny things start to happen, right? You start to be able to identify bottlenecks by looking at the depth of queues. So if you think about it in a messaging system, we can identify the bottlenecks in our architecture by looking at where queues build up in our message system, in our message broker, say. Well, the same thing happens with what we do in terms of the system of work we're in. We can identify bottlenecks in our process by looking at queues. And what we ended up doing with this, building this Lego set, was identify queues based on pages of the book. So each stage of the book, we put a bit of Lego ready to be assembled. The people finding Lego put some on the page of the book, then the people picked it off the Lego, picked it off the book. So we visualized this queue in the system. So often when you see storyboards, initially they might have to do, doing, done, which is useful. You're visualizing some bits of some work. But it's very useful to visualize the queues in your system, to visualize that ready for development as well as in development. And that's what we started doing here. We identified pieces ready to assemble as well as pieces being assembled. And the folks assembling the Lego, they pulled from the queue, and the people finding Lego pushed into the queue, much as a BA might do some analysis and push a user story into ready for development, and a developer will pull it out. That's another tip. Identifying queues in your system helps us in maximizing throughput in the system. In fact, queues are a leading indicator of throughput. They're a leading indicator of how fast you're going. Just by looking at how deep a queue is, if you've got lots of stuff waiting to be developed, you know the stuff at the bottom of the queue is going to take a long time to get into production, as opposed to the stuff at the top of the queue. So, we're at a conference. Bit of a sidebar here, based on conferences I've been to over the years. This is the idea that as a control measure, we can use queues as a leading indicator of how fast things are going. So if you think about going to lunch today, I think the time's wrong, I think it's after this. No, it is 1 o'clock, I think, today. So some people are going to be outside having a good time chatting with the sponsors, right? Some people are going to be in the talks. And we've got a bunch of places that are going to be serving lunch. So what's going to happen is the talk's going to finish at this point here, and a ton of people are going to start turning up to go for lunch. Right, you're all going to go, right, we'll go and get some food now. Let's go and get some lunch. So you've got a bunch of hungry people arriving at the food stalls. The problem is the food stalls can only serve food out at a constant rate. Right, so the number of people receiving lunch is constant. So you might see at conferences, sometimes you get this massive spike, suddenly everyone's standing in a queue, like, oh God, it's taken ages, right? It's taken ages to get lunch. Or in a supermarket, you have to stand, there's only 3 people behind the checkout, and there's loads of people queuing. This is a queuing theory problem. You've got variable rate of arrivals versus constant rate of departures. So your sessions finish, essentially the time it takes you to wait for lunch, it's going to be quite a long time. But if you just measure how deep the queue is, if you count the number of people waiting for lunch, you're aware of a problem much, much earlier than waiting for cycle time. And we got faster. By doing this, by optimizing the system, theory of constraints, adding queues, visualizing it, we got faster. So now we're into hours to build this thing, which is a good thing. That's the next tip. Use burn-up charts and yesterday's weather to track progress. But we didn't stop there. A number of funny things started to happen. The team became T-shaped. You might have heard of the idea of generalizing specialists on our teams, right? People who can do mostly development, but do a little bit of testing as well. For me, I'm a specialist in probably back-end distributed system design, that kind of stuff, building distributed systems, but I can do a lot of other things as well as a developer. I can help out our testers. I can probably turn my hand to enterprise architecture for a bit. Probably I could be a BA if I really needed to, but after 2 weeks, someone would find out I was rubbish at it and stop me, right? That's basically what would happen. But that's the idea of generalizing specialists. We want teams made up of these generalizing specialists, people who are good at one thing, deep in expertise, but broad across lots of different skills. And there's a reason for that, which I'll come to in a moment. So what we ended up with is a number of specialists in putting stuff together and a bunch of specialists who were good at finding things in our system of building Lego. This is true. If you think about it, if you're putting things together on a really big Lego set, the more you do it, the more you understand where the next bit's going to go. It's quite a difficult kind of topology, so I'm going to put this there. You get better at doing it. Similarly, with finding pieces, the more you look for stuff, then the next time you're like, oh, I remember where I saw that, I'll go and find it again. You get quicker at doing your individual role, at playing your individual role. And then those specialists noticed something interesting based on a control chart. They noticed that we had this massive amount of variability in how quickly it was taking to do stuff. So it turns out that finding a piece out of 5,000 pieces is a function of two things: how many of those pieces there are in the Lego set, and how big the piece is. So essentially something that's really small, and there's one of them, is much harder to find out of 5,000 things than something that's really big and there's lots of them, right? So the people finding things started to just-in-time optimize and start, if you like, caching pieces. So they started to create little caches of commonly used bits so that they could optimize for finding those little bits. We reduced the variability. We reduced the amount of time it took to find something, and also the variability of the system as a whole. The system became more predictable. We were more easily able to predict how long it would take to do something. So that's my next tip. Use control charts to identify variability in processes, and then you work to reduce that variability. So you can look at your development team and say, sometimes we're doing 3 points, sometimes we're doing 20 points. That's a big difference. That's a lot of variability in our system. Why is that? Why is it that sometimes we only get so few and sometimes we get loads? Is it because sometimes we're slicing the user stories up in a way that means we do lots of points and sometimes they're massive? Can we make sure they're all the same size, reducing variability? One of my colleagues, he's got three sizes he uses in estimation: snails, quails, or whales. Snail is too small, a whale is too big, and a quail, it's just right. It's like a small bird, if you probably have quails in Romania. Just right to eat, just the right size. Try and make everything into a quail. Reducing variability improves predictability of the system. Other interesting things happening. We had bugs. We started tracking defects. We used defect trackers. We had two types of bug. We had sort of cosmetic bugs, cosmetic defects. Oh, we can just move on. We just file the bug. We don't need to do anything about it at the moment. We'll take care of it later. That was maybe like a piece that made something look nice and shiny, but didn't need to be there for structural reasons. We didn't have to pause. And then we had structural defects. We can't find a bit we need to move on to the next stage. And that was like and-on chord. Stop the line. It's like the build went red, if you like. Our build was going red. Stop the line, everyone fix the build. Stop the line, everyone find the bit we need. Everyone swarm around the problem. And we also had work in progress limits. And there's an interesting and obvious, when you think about it, work in progress limit in our system of building Lego. And it's based on the pages in the manual. Because what we were doing is we were finding bits and putting them on the stage, finding bits, putting them on the stage, and then picking bits from the stage and building it. But if the people finding stuff raced too far ahead, They'd fill up the page of the manual, and then they'd be standing around. Because you couldn't turn the page because you'd lose all the Lego. The Lego would go everywhere. So we imposed natural work in progress limits on the system. Oh, sorry. And we also swarmed around problems. So if we'd found too much stuff and we couldn't find any more, those people finding things started helping putting stuff together. Similarly, if the build went red and we pulled the and-on cord, then we started looking for stuff. So that's my next tip. Limit work in progress, and as generalizing specialists, swarm around the problem, and in this case, pull work, or in every case, pull work from upstream to help. So in the development context, what that means is if you've got a massive backlog in testing, as a developer, what's the best thing I can do? Is it pick up a new story and write some code and add to the problem, add more stuff into the big queue ready for testing? Or should I try and clear that queue down, help the testers, because that means more stuff will get into production more quickly and we'll earn more money. So we swarm around problems and we go upstream to where the problems are. And so we got faster and faster and faster, and finally, woo, Chewie, we're home. There's the Millennium Falcon. We built it, we finished it. Woo, that's not the end, don't worry. But thank you. As I say, this is when the memes started happening, right? So, unicorns, woo! Hooray, everyone was really happy. So we did, we finished building this product. So one of my conclusions so far, so this is about 10 years ago, when we were working, using sort of mostly agile software development techniques. So my conclusion so far from this, the first thing is understand the system that you work in. Use systems thinking tools. Use things like value stream maps to visualize the process that you're in, to visualize the work that you're doing. And this, a value stream map is essentially, if you look at a build pipeline, it's taking your build pipeline and extending it all the way upstream to where requirements come from, and understanding how long all that sort of stuff takes. You might have come across the 4 key metrics from the State of DevOps reports, DORA. One of the 4 key metrics is cycle time from developer hitting commit to the code going live. That's an indicator of performance of an organization. But the problem with that is you could be infinitely fast at going from commit to live, but if it takes you 8 months from a requirement being created by the business to the code being committed, it still takes you 8 months to make any money. So understand the whole system. Don't just optimize the bit that you're in. Understand how to optimize the whole lot, the whole of the value stream. Visualize work. I mentioned the big problem that we have is work is invisible. If you're a manager in a factory, you understand where problems are, right? Because you can go and look at a machine and you can see tons of stuff waiting to be processed by the machine. There's a big load of inventory sitting there doing nothing, right? What we do, unless we visualize work, unless we use these tools, Kanban boards and so on, this work is invisible. We don't know if we're holding on to lots of inventory. We don't know if lots of stuff is stuck somewhere when it could be making us money or saving lives or doing what else we optimize for. The next thing is this idea of continually identifying constraints. Use the theory of constraints. Understand where the bottlenecks are and swarm around those bottlenecks. But understand also that it's like whack-a-mole. That's what I was forgetting earlier, whack-a-mole. The constraint will move. Just because you'll go in a bit more slowly in testing in QA this week doesn't mean that you're always going to be going slowly in QA. The bottleneck might move to analysis or to development or to waiting to put something into production. Using things like queues and work in progress limits and swarming around bottlenecks, they help in maximizing throughput and reducing variability. And that's a good thing because, again, it means we're improving the flow of stuff through our system, the flow of work through our system. And then we can understand progress using simple tools like burn-up charts, yesterday's weather, cumulative flow diagrams. Episodes 7, 8, and 9. They're like 4, 5, and 6, but just a few years old, right? Hi. So this is the only time I've ever been able to expense a Lego set. I thought I would do a sort of redux on this. What have I learned over the last 10, 15 years? What's the most important lesson that I've really learned? And funnily enough, it's the same lesson, it seems, that Lego have learned. So here's the question. If you were Lego and you were also constantly learning from building Lego sets, right? From the experience of building Lego sets, what would you do? What would be the change that would make the biggest impact to throughput, to our ability to put Lego together in the Lego system of work? And this is where I'll open up that as a question. Does anyone build Lego? Can anyone tell me what Lego does in the front? I'm sorry, I can't hear you. Maybe that was a rhetorical question then. There you go. Look at that. What would Lego do?
I can answer that, but I can tell you that I've built one when I was little, so I can't remember what it does.
Okay. Oh, back away from the monitor. Well, they did a funny thing, right? So if you remember at the start of this, I was talking about this massive Lego set. And what Lego used to do is they just used to put all the pieces in the box, just randomly assorted. So what you'd have to do when you were looking for bits, you'd have to search through 5,000 pieces. And it got easier as you built the thing, because 5,000 turned to 4 and 3 and 2 and 1. And when it was 1,000 pieces, it's easier to find things than it is when it's 5,000 pieces. Do you remember I said we started just in time grouping these things together? We created these little caches of bits that we knew we might need soon. Well, the funny thing is that Lego noticed that as well. So another science bit, the batch size queuing principle. Reducing batch size reduces cycle time. This is from a great book on product development, lean product development, The Principles of Product Development Flow by Donald Reinerson. If you read one book about how we do stuff, the economics of what we do as knowledge workers, as software developers, as technologists, people working in technology, this is Don Reinerson's book, Principles of Product Development Flow, is probably the one to look at the moment. The batch size queuing principle, reducing batch size reduces cycle time. And it's quite obvious to see, much the same way that if we reduce the number of people arriving at the lunch stalls, those people will get served faster. If we reduce the number of requirements that need to be there before going into production, those requirements will start earning money faster. If we've got large batches, we've got these large batches here, time in queue, quantity in queue. If we move from these large batches, maybe we're deploying once a month, to deploying every week, suddenly we've quadrupled the amount of stuff we're getting into production. And we've done nothing else. We've not added people. We've not added capacity. They're not working harder. We've just reduced the batch size. Because the sooner something's in production, the sooner it's earning money. And if something's sitting in a queue for a long time, it's not earning money. So reducing batch size improves throughput. Batch size reduction can enable us to shorten cycle time, often by an order of magnitude or more, without changing capacity or utilization. That's amazing. This is why continuous delivery works. This is why we reduce or increase the number of releases in our release trains, because the sooner something's in production, the sooner it earns us money. It's from the Principles of Product Development Flow. Don Reinerson talks about these problems that queues create. They lead to longer cycle times, because the longer, if something's at the bottom of a queue, it takes a long time to get to the top, if there's lots of stuff there. Increased risk. The longer a requirement is sitting in a queue, then the more chance there is that something will change, business context will change. You get more variability with deeper queues. You get more overhead in managing those queues, lower quality, and less motivation. As a developer, it's much more motivating for me to see my work in production doing what it's supposed to be doing a day later or an hour later than it is to wait 18 months for a big bang release. Much more motivating. So what would Lego do? Well, they reduce batch sizes. If you buy a Lego set now, what you get is a series of bags relating to a small part of the manual. They reduce the batch size so you can complete little bits, move on to a next little bit, improve your throughput. They've also, incidentally, got the memo about microservices. So microservices, a lot of that is about cohesion and reducing couplings. You allow people to work on things independently. Well, there's a thing from Don Reinhardson's book called the fluidity principle. Loose coupling between product subsystems enables small batches. And that's what Lego did. They enable you to build bits of these big sets and then plug them together afterwards, in much the same way that we can build our individual microservices and have them communicate via a uniform interface later on. That's the finished set that I expensed. So, my final set of tips. Understand your system, visualize queues, identify constraints in your system, and use the theory of constraints, but realize that it's limited, its limitations in product development. What do I mean by that? Well, I talked to you about the scout in the goal, the theory of constraints. You walk at the pace of the slowest scout. That's true in manufacturing, right? The machine can only do one thing. It can only build a thing and go as fast as it can go. So you subordinate all the other machines to the slowest machine. But it turns out in product development, humans can do more than one thing. So another solution to the scout problem would be to have some of the faster scouts go on ahead. Maybe gather some wood. Maybe put the tents up. Maybe make some tea. I'm British. I like tea. There are other solutions because humans are able to do more than one thing. Right? Swarming, helping out the QAs when there's a backlog in testing. We can solve problems in a slightly different way. But understanding where the constraints are, super, super important. Work in progress limits and swarming help keep throughput high. And this concept, if you take nothing away, small batches are directly related to cycle time. Controlling batch size is the best thing you can do if you want to earn money faster. And embrace anti-fragility. Don't always build microservices, but build things that can be independent and plugged together. These are the books that I guess I've been referring to over the course of this talk. This is what I've learned in 10, 15 years of agile software development, I guess. I've come to the conclusion that this thing around controlling batch size is absolutely the most important thing we can do. So software should be cheap to replace, quick to scale, resilient, and should allow us to go as fast as possible. Our system should allow us to go as fast as possible. So I asked myself, in that case, what would Lego do? They would use small batches. That's what Lego would do. That's me for today. Thank you very much. I'm going to be hanging out at the Thoughtworks store, so come and say hi. And yeah, thanks for coming. Cheers.